Welcome to my classroom. In this fuel cells and batteries course, in this module number 3, we have been discussing about high temperature PEM fuel cells, right? So in the past few lectures, we have been discussing about membranes for fuel cells, and we have seen what is a PEM fuel cell, what are the limitations of low temperature PEM fuel cells, all that, right? So in this, and we have seen about high temperature PEM fuel cells and what is the role of Nafion in it or alternative membranes that has to be used, right? So here now we are going to see some case study. Particularly, we will focus on what is the alternative to Nafion membranes available in the market, how we can incorporate some changes even in the Nafion membrane, or if not Nafion membrane, what is the alternative, how it is being prepared, and we will see a case study of how to prepare that particular membrane. Okay. So that's what we are going to discuss in this lecture number 13, the topic alternative membranes for high temperature PEM fuel cells. Before getting into this lecture number 13, let us see one important difference between monopoly and competitive market, because we are having a word polymer. You rearrange it somewhat, you will get this word monopoly. So what is this monopoly? What are the disadvantages associated with monopoly? We should know. If you look at the disadvantages of these monopolies, always we are going to have higher prices than in the competitive market. Actually, these monopolies face inelastic demand and so can increase the prices at their wish and giving consumers no alternative. Even if you look at this Microsoft in 1980s, what they did is, since they were monopoly on PC softwares, they charged a high price for Microsoft Office. So that should not happen, right? And also there is a decline in the consumer surplus because consumers pay higher prices and very fewer consumers can afford to buy this. It will also lead to allocative inefficiency because the price is greater than what is supposed to be the marginal cost, right? Monopolies have even fewer incentives to be efficient. With no competition, a monopoly can make profit without much effort. Therefore, it can encourage the inefficiency, which is called as organizational slack. So the laborers working there, they won't give promotion. There is no motivation to do much things, right? And if you look at even the possible diseconomics of the scale, a big firm may become inefficient because it is harder to coordinate and communicate in a very big firm, okay, big company. And also these monopolies have a monopoly power. What is this monopoly power? They are in paying a lower price to suppliers. For example, farmers have complained about the monopoly power of larger supermarkets, which means they receive a very low price for the products. A monopoly may also have the power to pay lower wages to its worker also, because there is no alternative company to people to jump, right? So also the raw materials they will buy at the very low price. That is the danger in allowing all corporates to get into this agricultural business also. Okay, so if a good government should not get into such type of corporates getting into thing and trying to become monopoly, and farmers will be getting very low price for it. Okay. And monopolies, on the flip side, what they do is they gain political power and the ability to shape the society in an undemocratic and unaccountable way, especially with the big IT giants who have such an influence on the society and people's choices. There is a growing concern over the influence of even Facebook, Google, and Twitter because they influence the diffusion of information in the society. They decide what you have to see, right? So based on your search criteria, based on the government, their collaboration with the government, they filter what the content they don't want to see or the government do not want to see, because there is no alternative. Facebook, no alternative. WhatsApp, no alternative. Twitter, no alternative. Because even though now there are many new things have come, but where the bulk of the people are there, it is difficult to come out of it, right? So that is the thing. They even keep on revising their privacy policy, make you to accept that thing. So that is the thing. And if you look at other company example, in the late 19th century, large monopolies like Standard Oil gained a notorious reputation for abusing their power and forcing the rivals out of the business. This has led to the backlash against the monopolies. But in the 21st century, there are many new monopolies which have an increasing influence on the people's lives. So that's what happened to your BSNL, Vodafone, Airtel, all that. The moment the Jio come into the picture, they gave the SIM card for free for several years. then others have to close it, they have to close and run. Then they started increasing the price like anything. Before this Jio came into picture, at least we used to have incoming call free, right? Nowadays you have to recharge even if you want to want to have incoming calls, right? So that is the problem associated with the monopoly. So this monopoly, if you want to avoid monopoly, you should have competitive market, right? So obviously there are some advantages associated with monopolies also, but here my concern is about the irregularities that is happening in monopoly, mainly with respect to we want to reduce the cost of the fuel cells, but what is happening with the higher cost of Nafion membrane, we are not able to reduce the cost, right? So that way, if you are able to reduce the cost by having an alternative membrane to Nafion membrane, so it will be easier for us to provide a low temperature, high temperature fuel cells. So particularly for high temperature PEM fuel cells, we want to have an alternative membrane which is cheaper than the Nafion membrane but provides a very good performance equivalent to that of a Nafion membrane. So that's why we are going to discuss this today's lecture, alternative membranes for high temperature PEM fuel cells when a particular monopoly is there. For example, in India, some of the monopolies are IRCTC Railways is a monopoly, even though there is a little privatization involved in it right now of late. Okay, so there are many other disadvantages associated with. You can go through it. So the reason there is a link to this monopoly to this particular lecture that we are going to discuss is in membranes also. There is a monopoly being enjoyed by the Nafion membrane because there is no better alternative to it for low temperature applications. So in that way, they are also enjoying some monopoly. So that is one of the motivation to find an alternative. So if you want to have a competitive market, if you want to reduce the cost, overall, if your end product means finally your electric vehicles on road price can be decreased, if you are able to find a cheap alternative or quality alternative to it, right? So that is there is always monopoly is always against the price. It will lead to always higher prices. So if you want to decrease the prices, so there should be a competitive market so that we have we can afford some of the electric vehicles in future. Okay. To start with this particular lecture, we have already seen in detail that proton exchange membrane fuel cells are considered to be the promising technology for clean and efficient power generation. And particularly for high efficiency PEM fuel cells, we need the polymer electrolyte membrane to be perfect. Okay, so that should have very good desired qualities should be held by it, right? Because this proton exchange membrane as the proton conductive material is a key component of the PEM fuel cell for transferring protons from the anodes to cathode, as well as providing a barrier to the raw material crossovers, right? So all this needs to be taken care by the proton exchange membrane. Okay, in the PEM fuel cell process at low temperature windows, 60 to 80 degrees Celsius, Nafion membrane was mostly used by the electrolyte and separated due to their several advantages. Okay. However, there are some disadvantages associated with this Nafion membrane, such as reduced carbon dioxide tolerance, low performance, humidification, and high expense due to low temperature operating temperature below 100 degrees Celsius, right? So we have seen in the previous lecture also what are the advantages of high temperature fuel cell. And if you look at this, particularly this Nafion membrane, which is primarily used in low temperature fuel cells, this is actually a perfluorosulfonic acid type membrane. And best known example for this type of membrane is DuPont's Nafion membrane. Okay, and that is being widely used in the research community as well as in the industries. And this Nafion is commonly used as a polymer electrolyte membrane because it gives high proton conductivity. They have excellent mechanical properties and they have provide us a good chemical stability also. Okay, but these high cost, low stability at the high temperature operations, low conductivity at low humidity conditions, or high temperature and high methanol crossover of Nafion. This limits the extent of its further application in the large scale applications. Okay, so there comes a question to avoid this monopoly or to if you want to have a low cost membrane alternative, what is the alternative to this Nafion membrane which can be explored? Okay, so that's what we are going to discuss in this lecture in detail. Okay, so here we are going to have a case study of what is the research status on high temperature PEM fuel cells, particularly on the alternative membranes that is being used as the used in place of Nafion membrane. So we are going to call it as Mpbi. What is that Mpbi is? It is the acid doped poly 2,2M phenylene 5,5 bibenzimidazole. Okay, bibenzenimidazole. So this is generally simply it is referred to as Mpbi. So we are going to discuss about this Mpbi in detail. Okay, because we should know what are the in the earlier lecture itself we have discussed something about this in short. Okay, so where we have discussed about what are the different membranes that are being used. So we have seen there are 4 type of membrane which is being used, out of which this modified perfluorosulfonic acid membrane is the first. These are the 4 membranes which are used for high temperature applications. Okay, so if you want to use at low temperature, Nafion membrane without modification, that is perfluorosulfonic acid membrane without modification will do the duty. But if you are high temperature applications, we need to modify this one because it has to deal with water in both liquid phase as well as in the vapor phase. So we are going to deal with modifying the perfluorosulfonic acid membrane. So first alternative is a modified perfluorosulfonic acid membrane, which was discussed in detail. We'll discuss again. So then we have sulfonated hydrocarbon polymer membranes. The composite membranes also being used. Another alternative is phosphoric acid doped or any sulfuric acid doped PBI, which we have seen now. So Mpbi. So PBI and ABPBI membranes and acid based membranes, all the 4 different type of membranes which are being explored towards high temperature PEM fuel cell applications. Okay, so what is this? First we'll just give a small intro to these 3 type of membrane, first 2 also, because before getting into 3 we should know what are the other 2. So modified perfluorosulfonic acid membrane means they basically consist of this perfluorosulfuric acid membrane, basically made up of PTFE backbone with perfluorovinyl ether side chains, which terminates with a sulfonic acid functional group, which are generally known as Nafion membranes. Already we have seen this in detail in the previous lecture. Okay, membranes for PEM fuel cells. Okay, so they are sufficient and they do good service for low temperature PEM fuel cells. But if you want to use them for high temperature PEM fuel cells, they are not suitable because they can easily lose proton conductivity at high temperature because of the glass transition temperature is around 120 to 140 degrees Celsius. Also, the evaporation of water molecules will be responsible for this proton conduction, right? So always we are going to use a modified PFSA membrane, which is attracting the attention for of the researchers, particularly for high temperature PEM fuel cell applications. So what modification can be done in this PFSA membrane? It can be done in the form of incorporating some hygroscopic inorganic material like SiO2, nanoparticle, morganite, zirconia, titanium dioxide, graphene oxide, and ionic liquids. Okay, then you have poly ETFE, then you have which can be grafted with poly-4-vinyl pyridine, P4PV, acrylic monomers, acrylic acid, and its associated polymers, inorganic heteropolyacids like phospho tungstic oxide, PTA, and layered double hydroxide nanoparticles. So any of them can be incorporated into the PFSA membrane, which is termed as modified PFSA. Even some of the membranes such as self-humidifying membranes like platinum on zeolite Nafion, PTFE and PBI composite, hybrid membranes, they have also been developed under this category. Okay, you can see some of the examples which have ionic conductivity of 53 millisiemens per centimeter at 120 degrees Celsius with 0% relative humidity. It can operate even at a high temperature of 200 degrees Celsius, where it is possessing some high thermal conductivity. Okay, so what is the difference here? 1 vinyl amidazole and 1 vinyl 2-pyrrolidone grafted ETFE membrane have been used. Okay, so in that case, they are able to perform with 0% relative humidity at 200 degrees Celsius with a 53 millisiemens per centimeter ionic conductivity. There are another Nafion graphene oxide membrane composite also being there. If you use a phosphate functionalized imidazolium ionic liquid, graphene oxide and Nafion membrane, so that also can be used. Okay, so such type of membranes, they are able to show some 13 times higher power density in comparison to the commercial Nafion 117 membrane. Okay, even when it is examined, they showed some thermal stability SIS 250 degrees Celsius, which is more than enough for a high temperature PEM fuel cell application, because the operating temperature is around 120 to 250 for high temperature PEM fuel cells. Okay. So another second type is the sulfonated hydrocarbon polymers under composite membranes. These SHPs under composite membranes, they have been reported to have a better mechanical and thermal properties, and they have some enhanced water uptake for a wide range of temperature. So even there are some examples for these SHP materials. Okay, so they are being used because they are having low cost, they provide high stability at the elevated temperature. So one of the example is a monomer with sulfonyl proxy side chains was prepared and then polymerized with bisphenol A and 4,4-difluorobenzophenone to form terminally cross-linked ionomeric blocks in the membrane, which showed high proton conductivity due to the unique structure. Okay, so that way this SHPs also can be used. Some of the other materials for HSP are listed here, you can go through it. So another kind of this hydrocarbon based polymer membrane is the modified ether based membrane, which includes aromatic polyether, polyether sulfone and its composites, or polyarylene ether sulfone and its composites, sulfonated polysulfone and its composites, sulfonated polyarylene thioether sulfone, and PA doped polytetraphenyl ether ketone sulfone. All these can be used under the Scanda category. Okay. So these are some of the examples for sulfonated hydrocarbon polymer SHP. Okay. So they have some other advantages. Okay. So now coming to our Mpba, because of the many advantages such as it will provide you faster chemical kinetics at elevated temperatures. Okay. So your chemical kinetics will be at the electrode will be taking place will be faster. It makes use of better heat utilization. It can be poisoning, catalyst poisoning can be reduced because it can tolerate more ppm of carbon monoxide, and simple thermal and water management. So this all has led to more research is expected in the development of high temperature PEM fuel cell, which operates at 100 to 200 degrees Celsius. Among that, this acid doped Mpba, that is poly-22M phenylene 5,5 bibenzimidazole, is a promising high temperature PEM fuel cell membrane because of its very high proton conductivity. It provides a very good thermal stability and its high fuel cell performance even up to a temperature of 200 degrees Celsius. So what we usually do is this acid doped, among various acids tried, it was reported that sulfuric acid or phosphoric acid are considered to be the doping agents in the membranes, which will act as both donors and acceptors in proton transfer and then allow the proton migration along the anionic chain. Among these two acids, if you ask which one is better, phosphoric acid has shown some interesting result because its conductivity, mechanical properties and thermal stability temperatures are greater than 150 degrees Celsius. Okay. So it can be easily operated above 150 degrees Celsius in comparison to sulfuric acid. So doping with phosphoric acid is one of the preferred operation. Okay. So if you look at the various type of phosphoric acid doped PBA membranes, there is an issue called acid leaching. Okay. So that problem, if you want to avoid that acid leaching problem of Mpba membrane, some unusual PBA composite have been studied. So what we can easily do is we will introduce some inorganic fillers such as phosphotungstic acid, silicotungstic acid, boron phosphate, zirconium tricarboxybutyl phosphonate, titanium oxide, titanosilicate, clay, aluminium oxide and silica. So any one of them can be introduced into the PBI membrane, which will drastically improve the ionic conductivity because there is it enhances the doping of the acid in the membrane. Also, it provides some long-term mechanical strength and thereby it avoids the acid leaching also. Okay. So by avoiding acid leaching, it provides a long-term mechanical strength. So to increase that mechanical strength, what we are doing is we are introducing some inorganic filler such as titanium dioxide or clay, aluminum oxide kind of material into the membrane structure. Okay. So what happens is these metal oxides are known to increase the proton conductivity of the membrane, and it shows very good affinity and interaction with the phosphoric acid. So that way this phosphoric acid, metal oxide membrane, PBA membrane, are providing us both higher proton conductivity as well as good improved mechanical strength at high temperatures. Okay. So even if you compare with the PFSA polymer, that is Nafion, which is mostly used in the PEM fuel cell, these phosphoric acid doped polybenzimidazoles are considered promising candidates for high temperature, around 100 to 200 degrees Celsius, because of the excellent thermal and chemical stability as well as enhanced proton conductivity. Okay, so if you look at these high temperature fuel cells which are operating at more than 100 degrees Celsius, they can provide very many benefits, such as it will provide, we have seen it in detail in previous lecture also, they are known to have higher catalyst poisonings such as CO tolerance. They can provide faster electrochemical reaction kinetics and high fuel impurity tolerance, which allows for simplification of the fuel processing system and possible integration of the fuel cell stack with fuel processing unit itself. So that integration will help us reducing in the design cost, space occupancy, all that, right? So from the proton conductive mechanism point of view, this phosphorus and phosphoric acid are amphoteric with both proton donor, that is acidic, and a proton acceptor, that is basic groups, to form dynamic hydrogen bond network in which protons can readily transfer by hydrogen bond breaking and forming processes. For acid-doped PBA membranes, there is a trade-off between the desired properties of the membrane, such as high proton conductivity and good mechanical properties. So it is a good trade-off it provides. Okay. For example, if you consider this Mpba membrane, which exhibits a very high proton conductivity at high doping level of even 13 to 16 moles of phosphoric acid, but the mechanical property of Mpba membrane with the same doping level is too worsened to use for PEM fuel cells. So even though you can have a very high doping level and have a high proton conductivity, but what happens in the other flip side is the mechanical property get decreased. So always we have to have a trade-off between this and that. What is that? Between the proton conductivity required versus the mechanical strength required. So that we have to consider carefully. If you look at this Jerem et al., what they suggested is maximum doping level of around 5 moles of phosphoric acid to maintain the reasonable mechanical strength of Mpba membrane for high temperature PEM fuel cell application, which provides us a conductivity of around 0.03 Siemens per centimeter. And if you compare this PPBA instead of Mpba, that is PPBA means it is poly-2214 phenylene 5-benzimidazole. Okay, so this shows superior mechanical strength because of the para-ordered molecular orientation and high molecular weight of the polymer. So what is responsible for this PPBA to have higher mechanical strength? It's para-ordered molecular orientation and high molecular weight of the polymer. Okay. And if you look at this Mpba, they may retain its mechanical strength with high doping level also. However, this application of PPBA in the PEM fuel cell is limited because it's extremely poor processability, as PPBA is only soluble in strong acids. Even though much effort has been exercised to improve the solubility of PPBA, such as incorporating of aryl ether linkage or M-phenylene linkage into PPBA backbone. However, this is only at the early stage, we can say. So there are reports which says that when you are adding such ether linkages or M-phenylene linkages, the thermal stability or the mechanical stability of the PPBA is compromised. That means it is reducing the mechanical stability and thermal stability. Okay. So what is this polybenzimidazole? This polybenzimidazole, actually they are a class of polymers which have incorporated in the structure the benzimidazole ring. So you can see this benzimidazole ring where you have NNH. Okay. So that is the polybenzimidazole. Actually they are showing some very good thermal stability, and they are able to retain their mechanical properties at the high temperatures. So these polymers are generally yellow-brown solids, infusible up to 300 to 400 degrees Celsius, and with some degrees of crystallinity detected in the more symmetrical types. Also, they have high resistance, height resistance, which makes them a good candidate for flammable resistant membrane, flame resistant membranes, and high temperature components. And these polymers show good thermal stability and retain their mechanical properties even at high temperatures. So that's why these polymers are preferred for high temperature PEM fuel cell. Okay. So this is the one of the presently available, which is commercially available polybenzeneimidazole, which is produced by the Celanese Corporation. Okay, so this poly 5,5 by 1H benzimidazole 2,2-di-113 phenylene. Okay, so this is the structure of this polybenzimidazole. So this is one of the commercially available Mpba. Okay. Now, this polymer is therefore one chosen most frequently by the researchers trying to find perfect applications of this PBI. So researchers have utilized these PBIs to produce some heat-resistant resins and fibers, structural adhesives, battery separators, mainly for aliphatic polymers and foams. Okay, so because they show good adhesion as films cast from solution onto glass, this quality has led to their use in glass composites and laminates also. Even woven cloth have been prepared using the Celanese PBI. The cloth is said to be comfortable due to very high moisture content, and they have high flame resistance also. Even certain PBI fibers have shown promises a reverse osmosis membrane, RO membrane also, it can be utilized. So these are some of the applications. Okay, so the use of PBIs as foams have also been investigated, and they provide a material having low weight, high strength, thermal stability. It is a machinable insulation that may find use in the aerospace application. So that is where these are some of the other applications of this PBI, and this commercially available PBI, which is given by the Celanese Corporation. Okay. So if you look at the properties of these polybenzimidazoles, they are somewhat hygroscopic and can retain moisture even at a very high temperatures like more than 100 degrees Celsius. Yet they are resistant to hydrolytic attack in acidic and basic media. They are generally of high molecular weight with a variation in molecular weight observed when the different methods of polymerization are used. Okay. And if you look at the solubility of these polybenzimidazoles, which is affected by the several factors, including what kind of solvent is being used, what is the molecular weight, what is the moisture content, and the operating temperature. So depending upon that, you are going to have different solubility of these PBIs. And in general, these PBIs are known to be soluble in acids such as formic acid, sulfuric acid, and aprotic polar solvents such as DMF. What is DMF? That is dimethyl formamide. What is DMFO? It is dimethyl sulfoxide. What is NMP? It is 1-methyl 2-pyrrolidone. And DMS, which is what is NN dimethyl acetamide. Okay, so improved solubilities have also been observed in the solutions of 1 to 5% of lithium chloride in the polar aprotic solvents. Even there are several demonstrations which show that this viscosity is decreasing in a lithium chloride solution, concentration in the solvent increases. Okay. So as the lithium chloride concentration in the solvent increases, the viscosity of this PBI is known to decrease. Okay. So that is the reason people have started working on these PBI based membranes. So if you compare to this modified PFSA or SHP based membrane, which you have seen in the beginning of this lecture, these PBI based membranes are generally preferred for high temperature PEM fuel cells because of their low cost, excellent chemical and thermal properties in the temperature range up to 250 degrees Celsius without humidity also. Okay. So there are diverse type of acids like nitric acid, sulfuric acid, perchloric acid, HClO4, HCl. They all can be doped into PBA membranes to work as the proton donor. However, among all, phosphoric acid, hereafter PA we will mention. So PA doped PBI membranes is known to have good conductivity, excellent thermal stability, and very low vapor pressure at the high temperature. But however, there are some issues associated with this PA doped PBA membrane, which includes catalyst poisoning due to the leaching of acid and membrane degradation due to the harsh operating conditions and the undesirable electrochemical reaction. Okay. So these are the background for this PBA based membrane. And with this PBA membrane, without any modification, there are many modified PBA membranes have been reported in the literature with enhanced performance. So some of them are like sulfuric acid doped PBA membrane, poly-2,5-benzimidazole based membrane, pyridine based PBA membrane, sulfonated benzimidazole membranes, polysiloxane doped PBA membranes, fluorine and fluoropolymer doped PBA membranes, aryl ether based PBA membranes, PBI and poly-2,5-benzimidazole ABPBI based composite membranes. Then you have phenylate containing PBA membranes, imidazole doped PBA membranes, polyamide benzimidazole based membranes, and methylated PBA membranes. So there are many other PBA membranes, among which we are going to focus on phosphoric acid doped membranes. So among all these membranes available, PBI, that is phosphoric acid doped PBA composite membranes, are identified to be the best for high temperature application for two reasons. Number one is they provide better mechanical and chemical stability because of the aromatic polymer background and the high glass transition temperature, which is around 425 to 436 degrees Celsius, whereas for Nafion it is around 120 to 130, right? So that is the increase, that is the major difference. And number two is higher proton conductivity, which is around 70 Siemens, that is 0.7 Siemens. 70 milli means 0.07 Siemens per centimeter, even at 160 degrees Celsius, and under dry conditions moving to phosphoric acid present in the polymer matrix. So that is the thing, when you are doping it the polymer matrix with phosphoric acid, it is able to give high proton conductivity of 70 millisiemens per centimeter even at 160 degrees Celsius. Okay, and also the performance of these PBA based membranes depend upon various parameters, including what is the amount and distribution of the acid present in it, what type of solvent is being used, what is the extent and type of cross-linking that has taking place between PBA molecules, and structural properties and morphology of pristine and acid-doped PBA. And if you look at the properties now, what is its water uptake? It is observed that 19 weight % of water it can uptake. This PBA based membrane can absorb up to 19 weight % of water, which is corresponding to around 3.2 water molecules per each PBA repeating unit. Okay. The issues associated with these PBA based membranes are, we should know now all the advantages we have been discussing. Let us be aware of what are the disadvantages associated with this. The issues associated with these PBA based membranes include acid flow out with the condensed water at temperature lower than 100 degrees Celsius when the high temperature PEM fuel cell device is not working. Then you have unsatisfactory mechanical properties under high temperature PEM fuel cell operating conditions, and we are going to have low proton conductivity at high temperature. Additionally, that acid leaching at low temperature will lead to chemical degradation of the polymers and other materials also. Hence, this acid doping level of PBA based membrane should be optimized for better mechanical stability and to minimize the acid loss during cell operation. Some of the strategies like covalent cross-linking and fabricating composite membranes also can be verified as being effective methods. Okay, so now I am just going to wind up with how to prepare a particular nano composite membrane, particularly calcium titanate PBA composite membrane. Okay, so this is taken from a research paper, recent paper. So it is actually a novel perovskite structured nano calcium titanate. It is depending upon the structure, we have a name called perovskite that you will learn in other course also. So what is perovskite? I will just introduce. It is nothing but a material that has the same crystal structure as the mineral calcium titanium oxide. So if you see the calcium titanium oxide, which is the first known perovskite crystal. You can see the crystal structure. There are three components here, A, B and X. Okay. So generally these perovskite compounds have a chemical formula of ABX3. There are three X molecules, atoms. So your A and B represents cation and X is an anion which that bonds the both. Okay. A and B are cations. X is an anion that bonds the both cations A and B. Okay. So there are several examples for this anion, cation, all that. The examples for A are Ma, Fa, Pb, Sn, fluorine, bromine, iodide, lead, tin. Okay, what is that MAFA? So MAFA is methyl ammonium is the MA. FA is formamidinium. Okay, so other than that you have CS, RB, which are being used as A material. So for B you have lead as a primary example, and X is chlorine, bromine or iodide. Okay, so these are some of the examples. So what is that? The methyl ammonium, you can see the structure here. It is like NH3 CH3. Okay, so here you can see the chemical structure of this methyl ammonium or formamidinium. So that is primarily used as A, either one of these two. Then B is mostly lead or tin is being used, and for X this iodine, chlorine or bromide is being used. Okay, so that is the structure for a perovskite. Okay. Now we are going to discuss about a novel perovskite structure, nanocalcium titranite PBA composite membrane. Okay, so what are the advantages of this Mpba? Just to reiterate, so they are known to have high proton conductivity, high thermal stability, and high fuel cell performance up to 200 degrees Celsius. And we can either use sulfuric acid or phosphoric acid as the doping agent in the membrane, which will act as both donor and acceptor in the proton transfer, and they will allow the proton to migrate along the anionic chain. Okay. So of the two acids, we have seen that phosphoric acid has shown interesting result because of its conductivity, mechanical property, and thermal stability greater than 150 degrees Celsius. This is the scheme of the reaction that is taking place in this Mpba preparation. That is, you have diaminobenzidine and isophthalic acid (IPA). So these two are under inert nitrogen condition, 220 degrees Celsius, polymerized to produce this polymer. Okay, what is being happening? Step-by-step procedure will be explained now. Okay, so what we take is, we have seen what is PPA, right? Polyphosphoric acid. What is IPA? Isophthalic acid. What is DB? Diaminobenzidine. Okay, so these names you should know that this is Mpba. Okay, how it is being produced? You will see DAB is 3,3-diaminobenzidine. IPA is isophthalic acid, and PPA is polyphosphoric acid. So these three are our raw materials. So the procedure we can explain here with this diagram for a flow chart. So first we can take 60 grams of PPA at 120 degrees Celsius. For this PPA, polyphosphoric acid, and it is mixed with 33.24 grams of 15.1 millimolar DAB, that is diaminobenzidine. Okay, so they are mixed well, and they are polymerized at a temperature of 200 degrees Celsius under proper mixing. So we allow the reaction to take place for 24 hours. So polymerization is taking place. So what happens? Polymerization, the polymer is formed. What will change in viscosity will be observed. So that is the indicator that the reaction is taking place. So the viscosity of the solution initial and final is going to be different, and we can observe that there is increase in the viscosity of the final product which is being formed. So what we do is, then we want to isolate the polymer. For that, what we do is, we use deionized water to the system. Okay, then this excess whatever is there, we have to neutralize it. Right? So whatever acid that is excess is there, so we neutralize it using some sodium carbonate. Okay, so then that final product is filtered, washed with water, again filtered and washed with methanol. So that kind of several steps of filtration is being done before we get the finally drying that one to get the product what we want. Okay, so we will get a polymer powder here. Okay, so once you dry this thing, we will grind it to make it a fine polymer powder. So this is the procedure to prepare your Mpba. Okay, so this is written, whatever we have told is written here. You can go through it. Okay. So what happens is, this whatever powder you get, the white powders are obtained from the gel by drying at 100 degrees Celsius in oven. The gel powder has to be fine, again calcined in air at a temperature up to 500 degrees Celsius. We call it a heat treatment. So that way we get this nano CTO PBA hybrid composite membrane, which can be prepared by solution casting method. Okay. For that, what we do is 2 weight percentage of Mpba solution in DMSO was mixed with the 5 to 15 weight percentage of nano CTO powder in an oil bath for 30 minutes at 120 degrees Celsius. So then that solution will be poured into petri dishes of diameter 17 centimeter. By drying at 80 degrees Celsius for 24 hours, we will get a final resultant membrane, which can be easily peeled off from the petri dishes, and then they were soaked in the distilled water at 80 degrees Celsius for 2 hours, and then dried further at 100 degrees Celsius for 1 hour. Okay. So this is what the procedure for preparing our materials. So what is that sol gel method? So the incorporation of this nano CTO, which is nothing but nano calcium titanium oxide, that is nano CaTiO3, which is prepared by sol gel method into synthetic Mpba, so that we develop a nano CTO PBI composite membrane. Actually, the macromolecular structure of this membrane shows the high conductivity and good oxidative stability. The acid doping level in this membrane was estimated to be by the amount of phosphoric acid per specific volume which is present. Okay. So the increase in the content of nano CTO will result in the increase in conductivity as well as the oxidative stability of the membrane. So thus these composite membranes are found to be potential electrolyte for high temperature PEM fuel cell with enhanced proton conductivity. Okay. So that is what completes this elaborate lecture on recent advancements in high temperature PEM cell, which is particularly we focused on alternative to Nafion membrane. Okay. So this is the procedure for preparing nano CaTiO3 PBI membrane, composite membrane. Okay. And if you look at the other list of high temperature membranes, so this table gives a consolidated report because from a literature, we have so many alternative membranes which have been reported in the literature. You can see the conductivity, temperature, what percentage RH they can operate. So these are the list of high temperature membrane and their properties. You can see you have Nafion composites, you have Nafion 117, you have recast Nafion. Apart from that, we are having Speak. Okay, there are 3-4 Speak on with other materials. Then you have SPI with fluorine groups. Okay, so you have conductivity, temperature, and relative humidity where they are applicable. Then you have SPIs, then you have PBIs, then you have PSU with pyridine hydroquinone groups. Okay, so that you can go through. Okay, so these are the properties of various membranes that have been reported in the literature. Okay, so for that each method there are different preparation method is there. So you can see that in this table where PBI doped with phosphoto tungstic acid and silico tungstic acid have been prepared on a gas diffusion layer using carbon cloth, where they prepare catalyst, platinum on Vulcan carbon, 28% anode for 48% in the cathode side. Then they use PBI binder, DMA solvent, auto. Okay, so that way they used it for different conditions, and what hot press method was used have been reported here. Okay, please refer to this also. So just to know what is PBI, as a homework you can try to write. You should be able to write here after what is PFSA, what is PBI, what is PEAK, what is SPI, and what is SPO, and you should be able to draw the structure. Draw the structure of PBI. You should be able to draw PEAK structure. So all these things you can practice well. Okay, so it's important for exam point of view also. Okay. So that's what I have wanted to conclude. So in this lecture, we have seen that a variant of PEM fuel cell which can operate at elevated temperature, which is known as high temperature PEM fuel cell, have been discussed. By changing the electrolyte from being a water based to a mineral acid based system, we are able to manipulate the membrane to operate at a high temperature up to 200 degrees Celsius, which helps us to overcome some of the current limitations with regard to fuel purity with the high temperature PEM fuel cells to process the reformate containing small quantities of impurities such as carbon monoxide. And even the requirement of balance of plant also being simplified by eliminating the humidifier. So you should now able to compare the low temperature fuel cells and high temperature fuel cells. So you should be able to write, compare and contrast low temperature PEM fuel cell with high temperature PEM fuel cell. So with respect to operating temperature, electrolyte, platinum loading, carbon monoxide tolerance, other impurity tolerance, what is the power density, whether it will start at cold or not, what about the water management, all that. Okay. Also, if I ask you to compare what is the structure, name A, B, C, and D, what is that? You should be able to name. Okay. So in the next lecture, number 14, we will discuss about high temperature fuel cells, which are solid oxide fuel cells and molten carbonate fuel cells. So one lecture on 2 will be following. Well, in this lecture, we have discussed about what is the alternative for a Nafion membrane. Particularly, we have focused on acid-doped PBI membrane, and we have seen what are the advantages and limitations associated with the Mpba, PBI, and even when you are incorporating some other materials, how it can provide us better proton conductivity and mechanical stability. And we have seen that it is always a trade-off between the proton conductivity and the mechanical strength. So accordingly, we have to have a doping of your acid level has to be controlled. Okay. Thank you so much for joining my classroom. Meet you in the next lecture with high temperature fuel cells. Bye bye.